Okay, so 3B starts out with two types of reactions. 3B is all about a couple of types of reactions. But it talks about two types of reactions that I'm hoping you guys have already seen before. Synthesis and decomposition.
Yeah.
Okay, so just to remind you, a generic synthesis equation, reaction, we're taking two substances, we're combining them to make another. So I have the example from the first unit, when we reacted zinc and iodine together and we formed zinc iodide. That's a synthesis reaction. Decomposition, just the opposite. We take a compound, we break it apart into two or more smaller pieces.
So with the when you have like two ionic substances and then you have like a flippy, does that give you, is that what's it called, synthesis?
A flippy?
Yeah, flippy.
No, that's
Double
single
replacement?
replacement.
Yeah.
Or double.
Double replacement is not usually considered
Well, I mean, if you look at the
synthesis.
net,
I guess from a net ionic
That's what
equation,
I-
maybe, yeah. Okay. So these are useful for stoichiometric reasons, right? Like when we actually calculated the empirical formula with this in that lab, we had to do some calculations with molar masses, we had to figure out the ratio, things like that, very closely related to stoichiometry. A really common example of a lab you might do with a decomposition is if you take copper sulfate, which is those blue crystals that we used for the penny lab, to make our known solutions of copper, and then we diluted it and diluted it and diluted it. We used copper sulfate, but it's actually the pentahydrate, so it had water molecules locked in with the copper sulfate ions. You can heat this, and you could split the water off and form just the dry anhydrous CuSO4 and water vapor. So that's a common lab where you take some mass of this, you heat it up, you figure out what mass of the anhydrous copper sulfate forms, and by looking at the masses, you can figure out how much water must have been in there. Okay, we don't have time to do that, but those are some common labs you might have to do. All right. What I want to talk about today are the two next types of reactions that are talked about in 3B. 3B2. Rochelle.
In a neutralization reaction, protons are transferred from an acid to a liquid.
Okay, who's heard of acids and bases?
Yeah.
Okay, way more people than in the last class. What do you know about acids and bases?
What
it's the concentration of hydrogen and
hydrogen
H
and
plus
hydrogen.
OH minus.
Okay, lots of things coming at me. I'm hearing pH.
The lower the pH, more acidic.
Lower the pH, more acidic. Higher pH, more basic. Okay, so those are some things. We have a way of measuring the strengths of acids and strengths. Well, really it's a measure of the concentration of the acid and base with pH.
Yeah, the acids have more hydrogen ions, the bases have more hydroxide.
Okay, so we think of something like HCl. That's an acid. It gives us H plus ions and chloride ions, which is what makes it an acid. It gives us H plus. We think about something like NaOH. It splits up into Na ions and OH minus ions. And normally think of the OH minus ions as what define a base. Okay? This is called the Arrhenius model. Acids give us H plus, bases give us OH minus. The problem with the Arrhenius model is it's very narrow. There's a very limited number of substances that can do either of these three things. There's a whole bunch more substances that we still consider to be bases that don't have any OH in them. There's actually acids that don't have any H in them as well. Okay, so we have some other models of acids and bases that do a little bit better job of explaining more different substances. So we're not going to use the Arrhenius model in this class. We're going to use the Bronsted model. In the Bronsted model, Bronsted Lowry model, what happens? Jagger, read 3B3.
When an acid or base ionizes it with 3
Oh, sorry, no, read 3B2.
When an acid or base ionizes in water, the
Sorry, just the essential knowledge, the very title.
Okay. In a neutralization reaction, protons are transferred from an acid to a base.
Protons are transferred. So in the Bronsted model, it's all about protons. We don't care about hydroxides. All we care about are protons. What's a proton? Well, H plus is technically a proton.
Yes, sir.
Hydrogen in its normal form is a proton, no neutrons in its nucleus, with one electron around it. If I pull that electron off to make H plus, all that's left behind is a proton. However, it doesn't really make sense to have a proton just floating off all by itself. Being so positively charged, it's going to be attracted to somebody.
Oxygen.
It's probably going to be attracted to the oxygen in water. So HCl, when it goes into solution, when it mixes with water, the H plus actually attaches itself to the water molecule. And so we form H3O plus. It's just like water, but with an extra hydrogen, H3O. And since that H that came off didn't have its electron coming with it, this species gets a positive charge, H3O plus. But what's left behind here? Cl minus. Okay, so that's the Bronsted model. In the Bronsted model, we had our acid, HCl, and we had to have somebody, since acids are proton donors, we had to have somebody to donate to. And in this reaction, we donated to water. So water's our base. All right. As far as bases go in the Bronsted model, well, let's think about a different base. NH3. Ammonia. Ammonia is a substance we know is a base. Well, how do we know it's a base? Well, if we react it with HCl, they can neutralize each other. So if we think about it on a pH scale, let's see. I've got some 1 molar HCl here. If I add some universal indicator to it, universal indicator is a substance that I left somewhere. I left it back over here. It's a substance that changes its color when it's in the presence of an acid or a base. So some people, I think I heard somebody say litmus paper, right? That's a piece of paper that's been soaked with an indicator so that when you put it into an acid or a base, it changes its color to tell you what the solution is. Okay, that's the color I'm looking for. Red. Universal indicator turns red in acids. In the last class, I used this bottle, which is labeled universal indicator solution. I put it in an acid and it turned green. I said, uh-oh, this is not universal indicator. So I got some fresh stuff out of the back. Okay, our acid turns red. Ammonia. I've got some ammonia. It's actually 2 molar, so I'm going to dilute it so that it's the same concentration as the HCl that I put in. Very, very quantitative dilution there. Perfect. Stoichiometric. All right. Let's put a little universal into our ammonia solution. Purple. Bases turn purple in universal indicator. It's beautiful!
Okay.
Okay, so that's part of the reason we know that NH3 is a base, because bases turn universal indicator solution purple. If I put NaOH, what we have here, if I put NaOH in a beaker and add universal, I hope it turns purple?
Yellow.
Purple. Okay. So NH3 is doing the same thing, wrong cap, same thing to the universal indicator solution as NH3 is, so we're considering it to be a base. Okay? But how is this thing acting as a base? What do bases do in the Bronsted model?
They accept protons.
They accept H pluses. Who's it going to accept an H plus from?
The acid.
Who's it got next to it in this solution?
Water.
Water. That's the only other thing in the solution. So it's accepting an H plus from water. What's it going to turn into?
Ammonia.
NH4 plus, the ammonium ion. It did that by actually pulling the H plus off of water. If water has its H plus pulled off of it, what remains? Hydroxide, OH minus. So there's actually some parallels here in the Bronsted model because we look at this base. Did the base have OH minus in it?
No.
No, so it wouldn't have fit in an Arrhenius definition, but because of the way it interacts with water, it ends up producing hydroxide in solution anyway. Okay? So it sort of is doing that similar thing to, well, it's similar result to the Arrhenius, but in a very different way. Okay, so here we're going to label NH3 the base, and we're going to label H2O the acid. As I said before, another reason we know that NH3 is a base is when I react it with HCl, they should neutralize each other. So add some of my base in there, and now I'll slowly add the acid. So now we're blue. I add just a little bit more. Still pretty blue. Oh,
Green.
sort of a blue-green.
It's supposed to turn green.
Yeah!
Green.
Okay, I wanted it to turn green because
Green is 7.
for a universal indicator,
Green is neutral.
a neutral solution should be green.
So that's safe to drink.
Heck yeah.
Is it safe to drink?
No. I mean, let's try.
Do you want to try some?
I know.
Well, define safe.
I already know.
I will
Not gonna kill you.
I had to.
Not going to kill you. Lots of things won't kill you that are not safe.
No, no, no.
Like a
Oh,
bullet
it's
to the-
not
like a bullet to the
gonna
hand.
die.
Bullet to the hand is not going to kill you.
Not gonna change
It's definitely not safe.
my body.
Excuse the.
It is going to change your body because when I react NH3 with HCl, well,
No.
I don't know if I want to go here yet.
Oh,
Well, sure.
oh.
As far as the reaction goes, sort of a double replacement, well, is HCl actually in there?
I mean,
What do you mean?
Was there actually HCl molecules in
No, it
this
was
solution?
that.
No.
Probably a
It's
couple.
already the
Actually, as soon as HCl touches water, it's going to form H3O plus and Cl minus. There are almost no HCl molecules in there. Very few, very little. Not enough to matter. Okay? So actually, when we react NH3 with hydrochloric acid, we're actually reacting it with H3O plus. There is Cl minus in there, but Cl minus is just going to be a spectator. H3O plus is going to transfer its proton to NH3, forming NH4 plus. And if it gets rid of its H plus, it's going to turn back into water. So is it safe to drink? Well, yes, we've sort of neutralized the acid-base properties of it, but we've still got these ions in solution. We've still got ammonium ions, we've still got those spectator chloride ions in there. So it's salt water. Is it safe to drink salt water? In small quantities, yes. In large quantities, it's going to dehydrate you and eventually.
Now, what would you call a
Large quantity, like, oh yeah, gallons for sure is good for that.
So I know that you would have us like label which one's the acid and the base, but would you ever have us like write down the equation? Like, let's say you wanted us to do NH3 and H2O. How do we know that it's NH4 instead of like H3O? Did I say H?
How do you know this thing's going to accept protons instead of donate them? You'll just have to learn some of the common bases. Okay, in the Bronsted model, typically the bases are going to have nitrogen on them. If you draw out this Lewis structure, you're going to see that NH3 has a lone pair, trigonal pyramid shape. That lone pair is just two electrons that are just waiting for somebody to go and make a bond with them. And it's the H plus that goes and makes the bond with the lone pair. So most bases in the Bronsted model are going to have nitrogen, some version of NH3. It might be CH3NH3, it might be C2H5NH3 or something like that, but it's usually going to end in NH3. Okay, so the more you do these, you'll get used to them. Okay. Now, there's a problem with one of these two equations that I wrote. That one, thanks. The second one has a problem. Uh-oh, missing an arrow. But why? Because when ammonia interacts with water, it does not 100% form these products. I can show that, hopefully, by comparing the conductivity of my HCl solution and my NH3 solution. Okay, so a strong acid, we should have both lights really bright, right? A strong base, we should have both lights pretty bright, okay? If these things are happening 100% to completion, we should have lots of ions in solution, we should be very conductive. If I try it with the HCl, see a bright green?
Green's not so much there.
Green's not bright, you see it on.
Well, if I point it right at you, you can see the green is on.
Oh, yeah.
Yeah.
If you missed it, watch the YouTube video. Okay. If I do it with the ammonium, or the ammonia solution, the green is like barely on at all, and even the red got a little bit weaker, right? So we call this a weak electrolyte. This does not happen 100% of the time. If you shrink yourself down to the size of a molecule, what are you made out of? But if you could do that, what you'd actually see is quite a few NH3 ions still in the solution. We call it a weak electrolyte.
When it's like
Okay. Weak electrolytes include things like weak acids and weak bases. HCl is not a weak electrolyte. We saw that the lights, when I put the conductivity tester in there, were very, very bright, showing that this happens nearly 100% of the time. 99.99999% of the time. Close enough to 100 that you are not really going to see any HCl ions left in the solution. Okay? There's 7 acids that are like that. We call them strong acids.
Strong acids or what?
Completely ionized in solution.
Okay.
Or completely donate their H pluses. So that if I'm going to write a reaction with a strong acid, I don't write it as HCl, I write it as H3O plus. Okay? You have to know what acids you're going to do that for. There's 7 of them. HCl is one of them. HBr is another. HI is another. Those would be halogens. HF is not though. That's the one in the list that is not considered a strong acid. And HAT, hat, you're never going to make enough hat to actually do this with, so you won't have to worry about hat. There's like 2 grams of astatine on the entire Earth's surface at any given time.
You gotta make more.
You make some more, and then you make me a 1 molar hat solution.
Hey, you didn't say, well, you didn't say how much solution it needs to be, so you can still make 1 mole.
That's true.
Yeah.
You can make, 10 to the minus 9th liters. A nanoliter of 1 molar, yeah, okay. Other ones. The stuff that I dissolved the penny with in the penny lab. HNO3, that's nitrate. What's another nasty acid you've heard of? H2SO4, sulfuric. And then perchloric, HClO4.
Phosphoric is.
And then, oh, sorry, this is perchloric, and then chloric is another one, HClO3. HClO4 and HClO3 are this strong acids. HClO2 and HClO are acids, but they're not strong acids, they're weak acids. Okay, those are the ones you have to remember. Strong bases.
Oh, hell no.
Any group 1 or group 2 hydroxide. So sodium hydroxide, potassium hydroxide, calcium hydroxide, yeah, francium hydroxide, you could collect enough to actually play around with it. Good luck. But it would be possible a strong base. Okay. The net ionic equation for the reaction of a strong acid and a strong base is going to look like this.
It's just a salt, right?
We're going to have H3O plus reacting with OH minus. Okay, again, whatever thing was originally attached to the hydrogen, it's going to be a spectator. So if it's HCl, Cl is going to be a spectator. If it's HBr, Br is going to be a spectator. Whatever group 1 or group 2 metal was originally attached to the hydroxide is also going to be a spectator. So if it's sodium hydroxide, the sodium, we don't care about it. Potassium hydroxide, we don't care about the potassium. Okay, it's just the OH that matters. What's the product going to be?
2 waters.
2 H2Os. Why? Because we're still thinking about the Bronsted model. In the Bronsted model, this is going to donate its proton. If it donates it, it's got to donate it to somebody. It's donating it to hydroxide. When it does that, we're going to be left with H2O.
Wait, what's that thing called again when you have the H3O? I forgot what it's called.
Hydronium?
Yeah, that.
This is the hydronium ion. When this gives its H plus to hydroxide, we form another H2O. Okay? So it's actually pretty similar to the way that the Arrhenius model works. In the Arrhenius model, H plus and OH minus combine to form water. In the Bronsted model, we're still forming water, but we're forming it from H3O plus and OH minus. So this is the net ionic for a strong acid, strong base reaction.
Wait, just a sec. So like, you got like a chloric acid or like sodium hydroxide on. Are you not forming a salt?
You are forming a salt, but the salt is going to be soluble. This is the net ionic equation. That salt is still going to be in there, but it's not going to appear in the net ionic reaction. Okay. Now here I actually reacted a strong acid with a weak base. So again, if it's a strong acid, we treat it as H3O+. Weak base, we're going to treat it just like whatever the original form is. A weak base is not going to split up in any way, so we're just going to treat it like the original molecule that we were given. All right, let's look at one. Let's look at a strong base. with a weak acid. So an example of strong base, NaOH, but is it really NaOH?
Oh,
No, it's just OH minus. A weak acid? Well, I've got a weak acid here.
phosphoric acid.
Phosphoric is weak. I'm going to use acetic. Yeah, the acid that makes up vinegar solution. C2H3O2. What happens when these combine?
Water and acetate.
Osama, read 3B2.
Wait, which one?
Essential knowledge 3B2.
Okay. In a neutralization reaction, protons are transferred from an acid to a base.
So, what's going to happen in this reaction?
The acid mix.
Protons are going to be transferred from the acetic acid to hydroxide, the base. When a proton is transferred from acetic acid to hydroxide, what's this going to become?
Water.
H2O. And when acetic acid gives up its H+, what is left behind?
Acetate? Or whatever it's called.
C2H3O2, the acetate ion. Alright, so this is aqueous. This is aqueous. H2O is a liquid. C2H3O2 is also aqueous. How am I going to split this up though? Should I make this a net ionic equation?
This one down.
This actually is the net ionic equation.
Yeah.
Because this being a weak acid, it doesn't totally split up into its ions.
Wait, do we have to put the other? Yeah.
So we actually need
What are we not going to do with that one?
this one?
Yeah.
Yeah, we can deal with this. Now, in reality, the arrow is actually mostly this direction. in these
Well,
type of reactions.
that's for when we get to equilibrium.
In equilibrium, we'll actually be able to calculate whether this thing is product favored or reactant favored. These two, the weak base strong acid reaction, the strong base weak acid reaction, those are pretty strongly product favored. For right now, what they want you to be able to do, it talks about in part B3, when an acid or base ionizes in water, the conjugate acid-base pairs can be identified and their relative strengths compared. Okay, so when it ionizes in water. So let's go back here and let's talk about this weak base ionizing in water, where we have the double-sided arrow. I labeled this NH3 a base. This reaction can happen in this direction, NH3, except a proton, it forms NH4+. But if we drew the arrow going the other direction, that means NH4 can do, NH4+ can do what? It can actually donate that proton back to OH minus and turn back into NH3. If it donates its proton, it's being an acid. But because it's an acid that came from NH3, we call it a conjugate. So this is a conjugate acid. It's what the base turned into after it accepted a proton. Hydroxide in this reaction, it can accept a proton from NH4+, which makes it a base, right? Bases accept protons. But because it's a base that came from something, because it's a base that's on the product side, we call it a conjugate base. It's the conjugate base of that acid H2O. And it says the relative strengths can be compared. The relative strengths. So we've got two acids in this reaction. What do acids do again, Hope? what do acids do?
Donate protons.
Donate protons. Man, look at her.
Thinking of chemistry in her sleep.
Right, she was reading.
It's the best way
Okay.
to breathe.
So both of these things have the possibility of donating a proton, right? Who's better at it? Who's better at donating their proton? H2O or NH4+.
Good question. I would go with
H2O.
H2O.
You said it's acid.
We can't answer that question unless we know which of these two things we're more likely to find in solution. We have to know whether this reaction is going to end up more with the products that I've written or whether it's going to end up more with the reactants that I've written. Right? Which I didn't tell you. Or did I?
Yeah, you did. You said it's product type.
I said it's...
Product type.
Did I?
Yeah, you said for both of them.
No, I said when I put the conductivity tester in here, we didn't get a very bright light.
No, but for the reactor, you just said right there.
This is not reacting with water. Here it's reacting with
Oh, okay.
H3O+. Okay, so that's a little bit different. We don't know what the product favored or reactant favored of that is just by looking at it, so we'd have to calculate it. But I know because, you know,
Because you're
one of those
chem prodigy.
teacher dudes. Teacher dudes.
Why it's gotta be a dude?
So let me see. Let me see if this simulation is going to help us. Okay, so here's a little magnifying glass look at some different solutions. So, here's water. Actually, there's the water.
Oh, Lord.
In gray are all the water molecules. It turns out that water itself, because water, take a look at these two reactions. I labeled water a base here and an acid here.
Yeah.
You can do both.
Yeah, because it's neutral.
It's amphoteric. It can accept protons or it can donate protons depending on who it's mixed with.
As long as you can spell that.
You're gonna spell that?
Amphoteric, it's on your outline.
I only just AMPHO.
3B2 Part A. The amphoteric nature of water plays an important role in the chemistry of aqueous solutions, since water can both accept protons and donate protons to dissolved species. It turns out water can do it to itself. When two water molecules collide, one can give up its proton, the other one can accept the proton. And so when H2Os collide, sometimes we actually just produce H3O plus and OH minuses in solution. So when you guys think of water, you think it's neutral. What does that mean? pH is 7. Is it an acid or a base?
Neither. Both.
Both is the correct answer. You cannot have no H plus in solution, because water will actually collide with itself and give you H3O plus. You cannot have no base in solution, because water can collide with itself and give you OH minus. But it turns out that at a solution that's a pH of 7, you have equal amounts of H3O plus and OH minus. When I reacted these very strong, the strong acid and the weak base together, I produced a neutral solution. Doesn't mean there's no acid or base in there. It means I had equal amounts of acid and base. Most of it neutralized, but there's still some water that can split up and give you these two. Okay? We'll talk way more about that when we get into equilibrium, but what I want to show you is a strong acid. Okay? The strong acid here, the molecules of strong acid are these dark gray ones. Do you see them in the solution? No, let me turn off the solvent. Let me turn off the water. There are no dark gray molecules in there. HCl, again, when you look at HCl, you will never see an HCl molecule, because the HCl completely gives up its proton, and so what you really see is H3O+. That's why we write net ionic equations. If we have a strong acid, it doesn't make sense to say HCl. There's no HCl in it. We say it's H3O+. And of course, you've got that spectator of the A minus. It could be Cl minus, it could be Br minus, NO3 minus, any of those anions of these strong acids. Now, if I look at a weak acid solution, what I actually see is primarily acid molecules, right? I see lots of these little dark gray ones, very few of the H2O pluses and the other ion of the weak acid. So that's why when we write a net ionic equation with a weak acid, typically we keep that acid together. We don't split it up into its ions. Because if we look in solution, we're going to find mostly those molecules still together. All right? Same situation. For a strong base, we don't find any NaOH molecules in there. They're all split up into OH minuses and Na pluses. But if I look at a weak base, in a weak base, you have mostly the base molecules left behind. This is a monoatomic base. I'd have to think of what it could possibly be.
Sodium. Just sodium.
But it's primarily those molecules still together. So that's why when I wrote the net ionic for the weak base, where was it? Here, I didn't change it into any form, right? Because I assume most of it is stuck like this until some reaction occurs. All right? Before we're done here, let's do a quick little identification of acid-base, conjugate acid-base pairs. For this reaction, who's the base, who's the acid?
Oh, ammonia, the base,
H2O plus is the acid. Who's the conjugate base?
ammonia.
The conjugate base is not the thing that the base turns into. It's the thing the acid turns into. So H2O is the conjugate base. Why?
Because receiving the proton.
In this direction, it gets protons. And proton getters are bases. The base turns into NH4 plus. In this direction, NH4 plus gives up its proton, turn back into NH3. So that's a conjugate acid. Okay, so those are the things you're going to have to do on your problem set. Yep, take a quick break, everybody.